Hello everyone. Today we're going to do a few examples with our friend the hover disk, right? And along the way we're going to try to figure out if there's a relationship between the type of motion of the hover disk and the forces that are acting on the hover disk. Right? And along the way we're going to learn a new technique, a new model if you will, for showing those forces other than the system schema, which we're still going to do. Right? But then we're going to build a new kind of model as well. So our first example is pretty straightforward, at least in terms of the motion. The hover disk is just sitting on a table. It's not turned on, right? It's just sitting there. So I want you to take a mental picture of that hover disk. We're going to do this in each example, okay? Are you ready? Ready for your mental picture? There we go, right? You took a little mental picture. So let's do a quick little system schema here. Right, we have the hover disk. What is it interacting with? Well, of course, it's interacting with the Earth as a whole through the force of gravity. Always an interaction between the object and the Earth. But that's not it, because otherwise the hover disk would fall. So there must be something supporting it, which is, of course, the table it's sitting on. We call that support force, which would act perpendicular to the surfaces, the normal force. And if you remember, that comes from the hover disk slightly deforming or compressing the table, and the table trying to go back to its original shape, right, and supporting it. And that's pretty much it, right? The hover disk doesn't really interact with anything else. So our system here is just the hover disk. And you'll notice that there are two interactions taking place, two forces. The system schema is good at helping us identify the interactions that take place. Okay, but it doesn't really show us a lot about the forces. So instead we're going to use a new model, new technique, which is called a force diagram. Or back when I learned it, it was often called a free body diagram. This is where we're going to draw a little picture of the object, a very simplified picture, and then on that we are going to draw a representation of all of the forces that act. So let me draw quickly here a representation of the hover disk, but a very simplified one. I mean, why spend more time than that? Sure, you could draw a circle like we did here. You could, draw out an actual hover disk like I did up here, right? But the dot is just traditional. It just, kind of reduces what we're doing here. Right? We're treating it kind of like it's a particle. So what forces act? Well, let's look at our system schema. We've got the force of gravity, which acts in what direction? Yeah, it acts down. And that means that we need to be able to show two things when we draw these forces. We need to be able to draw their magnitude, their size, and we need to be able to show the direction they're acting. Because forces are vector quantities after all. Well, as we've done in the past, when we wanted to draw a vector, right, we did a whole unit on this, we drew it as an arrow. Right, so we'll do that here. We will draw a downward pointing arrow for the force of gravity. Notice how the arrow starts on the dot. We're going to draw all of the forces will always start on the dot and radiate outward. Okay? It's just the way you draw the diagrams. You start on the dot and radiate outward. So again, here's the force of gravity. The length of this arrow represents the magnitude or size of the force of gravity acting on the object, or its weight. Okay? And the direction it's pointing is the direction the force acts, down towards the center of the Earth. We also have this support force, this normal force. Well, what direction do you think that acts on the hover disk if it's supporting it? Yeah, it acts up. Right? Again, length representing the size, direction representing the direction. Right? And notice that we label these, right? These are arrows, not line segments. These are vectors, right? And we put what they are next to them so that we can identify them. Right? Always have to label your force diagrams. Now the question becomes, well, how big is this normal force compared to the force of gravity? And I don't want an actual number here. I'm just looking for it to compare to gravity. What is your intuition telling you about this? Well, let's consider for a moment what's going on with the hover disk. It's just sitting there on the table. Does it have a constant velocity or a changing velocity? And that's as complex as I want the terminology to be for now. Is that a constant velocity or a changing velocity? It's just sitting there, right? So it's a constant velocity. Although a special constant velocity, 0, because it's not moving, but that's still constant, right? Because it's not changing. So what does your intuition then tell you should be true about the size of these forces if the object's just going to sit there? Hopefully you're saying, well, maybe they're the same size. Maybe they are, in fact, balanced forces. Maybe the normal force is the same size as the force of gravity. Now, I'm showing that over here in symbols. Note that I did not put arrows on these because these are not the exact same vectors. Even if we decide they're the same length, one's pointing up and one's pointing down, right? So by taking the arrows off, these are just scalars. They just have a magnitude. So this is just saying the normal force is the same size as the force of gravity. And notice on the actual diagram, I drew these little hatch marks, right, which you've used in geometry class to mean they're the same size, right? And you see these sometimes in force diagrams, sometimes not. I kind of like using them more recently because it just makes you think a little bit about it. So you okay with that? With the normal force and the force of gravity having to be the same size because it's just sitting there? It's got a constant velocity? We're looking for patterns here, okay? So there's our first example. Our second example, going to turn the hover disk on and give it a little push and then let it move across the table to the right. Now, I want you to take a mental picture of it when it's about here. You with me? When it gets to be about here, take a mental picture. Ready? Let's watch it again. And think about how we've seen a hover disk move. So, these little things are like cartoony things, meaning it's moving, right? So right at this point, it was already moving. I'm not talking about over here, okay, when I was pushing it to get it going. I'm talking about when it was way over here, right? Okay, so let's be clear about that. That's why I put the picture here. So let's do a little system schema. We've got the hover disk. What is it interacting with? Of course, the Earth through the force of gravity. Is it being supported? Yeah. Right? But be careful here. Is it actually touching the table or the floor? No. Right? The hover disk rides on a little cushion of air. Right? So there's a little cushion of air that it's on top of. That's what's actually supporting it, is the air, not the table. So just to be specific here, I'm going to call that a normal force. I could call that a force from the air, but it is a support force after all. Okay with that? So be careful. It's the air. What about me? Am I interacting with the hover disk? Well, now be careful. Sure, at some point in the past over here I did, but I'm talking about when it's here, when we took our mental picture. Am I still touching the hover disk? No, right? I am not. And is there friction? Well, no, right? That's the whole point of the hover disk. If we neglect air resistance, and if we neglect that, then the whole point of the hover disk is it rides on this little cushion of air instead of rubbing against the tabletop and sliding across the tabletop, right? And therefore, no friction either. So that's it. It's actually a simpler system schema than it may look. So if the hover disk is our system, let's draw a force diagram. There's the hover disk. And again, remember, we're looking at it when we took the mental snapshot. We've got a force of gravity, which would act downward. We've got a support force, a normal force, which would act upward. Hover disk have a constant velocity or a changing velocity? Hopefully you remember the whole point of the hover disk was to have that it moves at a constant velocity because it has inertia. It has a tendency to just keep doing what it's doing. So how big do you think this normal force is compared to this force of gravity? Well, my hypothesis here is that, again, they are balanced with one another. They are the same size. Now, think about this for a minute, really, because you might be saying, but wait a minute, this looks the same as the last one. And it does. Right? It looks like the exact same force diagram. Right? But one was moving and the other one wasn't. True. But they both had constant velocities. So we'll consider this as we move on here. okay? Also, think of it this way. The hover disk was moving horizontally. Was it moving vertically, where these forces are? No, it wasn't, was it? It wasn't moving vertically, only horizontally. Interesting. Okay, third example. This time I'm going to turn the hover disk off and give it a push and let it slide across the table. And again, I want you to take your mental picture somewhere out here. You ready? Yeah, don't ask me about that sound. It was the best thing I could find, all right? That's the hover disk sliding against the table. Watch it again. Mental picture out here. You see this is different than the last one, yeah? Okay. Again, here we're looking at it, and it's still moving at this point, right? So here's our hover disk. Again, it interacts with the Earth through the force of gravity. It interacts with the table because the table is supporting it, right? That's a normal force, otherwise it would fall. But there's something else going on here, right? It's actually sliding and rubbing against the table. And when that happens, we get another interaction with the table. We get the force of kinetic friction. Okay with that? Right? Now, no force of tension. I'm sorry, tension. No force from me because we're looking at this way out here. Right? Not when I was first pushing it, right? But when we took the mental snapshot out here in the middle. So, hover disk is our system. Let's draw the force diagram. There's our hover disk. We've got a force of gravity which would act down. We've got a normal force which would act up because it's a support force. And then we've got this force of friction. Well, the hover disk is sliding to the right. So what direction do you think friction would act? Yeah, to the left. Right? Friction opposes motion. Now notice the normal force and the force of gravity are going to balance each other out. Why? Well, like we talked about with the last one, it's not moving up and down, right, at all. So these have to stay in balance, right? Just like our first picture. But, horizontally at least, did it move with a constant velocity or a changing velocity? Yeah, this time it was a changing velocity. Now look at the force diagram. Are all of the forces balanced? Well, the normal force and the force of gravity are balanced, but is anything balancing friction? No, right? I'm not pushing on it at this point, right? There's no string or anything attached to it, right? So, no, these forces are unbalanced. Right? Unbalanced forces. There's some extra force there that's not balanced out by anything. You with me? Interesting. Looking for patterns. One more example. This time I'm going to turn the hover disk back on so it'll be riding on a little frictionless cushion of air, and I'm going to pull it across the table with a string. And I'm going to try to pull with a constant force, okay? Pull with a constant force with the string. Now watch what it does. And again, out here, you're going to take a little mental snapshot. Ready? Watch it again. Watch what's happening here to the hover disk. Right? What's happening to it? Yeah, it's speeding up, right, as it's being pulled. Yeah, it's speeding up as it's being pulled. So let's keep that in mind as we do the rest of the problem. So, again, we're looking at it in the middle here somewhere, right? It is moving. Here's the hover disk. What's it interacting with? The Earth. Hopefully by now that's just become something you're used to through the force of gravity. Is it being supported? Indeed it is. Right? But this time by the air because it's turned on. So that would be a normal force, a support force. Friction? No, right? Because it's on, so it's riding on the little cushion of air. We're going to neglect any air resistance effects. Well, is it interacting with anything else? Sure. Right? It's interacting with the string, right? The rope. Now, what do we call that force? Remember? Forces exerted by strings and ropes and wires, chains. Yeah, we call those forces of tension. F sub capital T, right? So there's a force of tension here. What about me? Am I interacting with it? Be careful. Am I actually touching it? No. Right? I'm interacting with the string, so sure, you could put a circle with me out here, but then there'd just be an interaction between me and the string. Right? And if we're going to focus on the hover disk, is that important? No. It's no more important than the floor supporting the table, right? Which again doesn't really do anything to the hover disk. It's one step removed, if you will. So we just want to focus on the hover disk here. So let's draw the force diagram. There's the hover disk, force of gravity acting down, normal force acting up. Guess how big they are since it's only moving horizontally and it's not moving up and down? Yes, they are the same size. That won't always be true, right? If we're on an incline or if we're moving up and down like in an elevator or something like that. But for our examples, it is. And then we have the string, which is going to pull in what direction? Yeah, it's pulling to the right, so there's the force of tension, and there's no friction. Well, did the hover disk have a constant velocity or a changing velocity? Yeah, it was speeding up, right? So it had a changing velocity. And are these forces balanced or unbalanced? Well, the normal force and gravity are balanced, but there's nothing to balance out the force of tension. So this is an unbalanced forces. You see the pattern? Well, let me help you here. Let's summarize. Okay? Pattern between the type of motion and whether or not the forces are balanced, right, is what we're trying to figure out here. So here's our first example, right? This is when it was just sitting on the table, constant velocity of 0, forces were balanced. Moving across the table with a constant velocity with no friction because it was riding on the little cushion of air because it has inertia. Constant velocity, balanced forces. Third example, turned it off, slid it across the table. Now it was slowing down, so it had a changing velocity because of friction, and it had unbalanced forces. And then the last one, this is where we turned it on and pulled it across the table with the force of tension from the string, and it was speeding up, so it had changing velocities and unbalanced forces. You see the relationship, I hope, right? What has to be true about the forces for something to have a constant velocity versus a changing velocity? Well, this was first discovered by a guy that we're going to spend a lot of time talking about over the course of the year since we're studying the mechanics named after him, Sir Isaac Newton. A couple of cool things about his date of birth. First off, 1642 is the year that Galileo died. The year Shakespeare was born as well, I believe. So Galileo dies, Newton is born. Kind of interesting. The other neat thing, he was born on Christmas. Aw, Isaac Newton was a Christmas baby. Now, you do have to be a little bit careful with that, okay? Sometimes if you look this up, different biographers will list different dates, and that's because there was actually a calendar change between 1642 and now. We're now on the Gregorian calendar. Back in 1642, England was still using the Julian calendar and hadn't switched yet. And so under the Julian calendar, which is the one they were living under, it was Christmas. But if you actually take our calendar and work backwards, you'll end up on a day that's not Christmas. I like the Christmas day because I just think it's neat, right? So that's why I use it. But you might see it a slightly different day if you're using our current Gregorian calendar. Right? They changed calendars to try to make everything fit our orbit around the sun and such. So 1642, the year Galileo died, on Christmas Day. Isaac Newton took this idea that we just found, right, this little pattern, and he named it his first law of motion. There are three of laws that we are going to eventually talk about. This is Newton's first law of motion. These laws are kind of the basis of understanding Newtonian mechanics. They're super important when it comes to understanding why things do what they do. So here's kind of what we came up with. Objects move with constant velocity when the forces are balanced. They move with changing velocity when the forces are unbalanced. We're going to actually do these kind of in two different units, okay? We're mainly in this unit going to be focusing on when things are balanced. We'll do a few more conceptual looks at when things are unbalanced, like we just did, right? But then we'll look at a whole different unit, what happens when things are unbalanced, okay? But this is not the way Newton wrote it. If you look it up in his Principia, which was written in Latin, right, his big book of mechanics and things, right, he wrote it more like this if you translate it. An object will continue in its same state of motion unless acted upon by a net force. Now, take that sentence apart a little bit. An object will continue in its same state of motion is really just Galileo's law of inertia, right? He was just using that idea that objects, the masses, anything that has mass, it has a property that it will continue to do whatever it was doing. Objects at rest stay at rest. Objects in motion tend to stay in motion. Right? That's what it means by same state. That's the law of inertia. But what what Newton realized is how you could then change that motion. Right? That required what we call a net force, an unbalanced force. Okay? The forces have to be unbalanced. Either, like in our examples, there's one and there's nothing opposing it, or if there is something opposing it, they're not the same size. Right? One's bigger than the other. So there's something left over, if you will. And that's why we define a net force to be the vector sum of the forces. Vector sum means we add them up with directions, right? Which is, of course, what we spent a whole unit doing or building towards. So we can do vector sums now. Right? So vector sum of the forces is what is called the net force or the resultant force or the unbalanced force. Okay, so it's this idea of inertia, Galileo's law of inertia, but with this little bit added on. Now realize this, of course, completely against the Aristotelian viewpoint, which was kind of the opposite, that thought that you had to impose violent motion upon something to get it to move, right? That things don't just move on their own, right? They have to be forced to move. Well, both Galileo and then Newton realized that an object that's moving just tends to keep moving on its own. You don't need to do anything to help it along. You just have to put everything in balance. Newton was once quoted as saying something along the lines of, "If I have seen further than others, perhaps it is because I have stood on the shoulders of giants." And certainly, one of the giants that Newton was talking about was Galileo Galilei. Right? Without this idea of inertia, right, we wouldn't have Newton's first law and so forth. So in this unit, we are going to spend a bunch of time then looking at situations where the forces are balanced and the velocity is constant, or they're unbalanced and the velocity is changing, or vice versa. Right? And drawing force diagrams, and for a while at least system schema, right, to help us see what's going on, and to actually eventually even do some math about what's going on and make some predictions of what we need in order to make things move this way, right? It's kind of where we're building.